Hello, everyone. That was quick. You guys settled down very quickly. I'm impressed. Good afternoon. My name is Ken Goldberg. I'm a professor here in the College of Engineering and also very connected to the various projects that are going on here at the Center for Information Technology Research in the interest of society. So it is a great pleasure for me to welcome you here and also welcome all of the people who are watching this on the web. I'm thrilled to see that robots are as appealing as ever and still bringing in a huge audience. There is a couple other things scheduled. As always, Yvette has got a full schedule of talks and events. They're all listed on the CITRIS website. Particularly, there's the I4 Energy talks that will be coming up on Friday. And I have the distinct pleasure of introducing Steve Cousins. Steve, I've known for many years. I've admired his work. He did some work at that other institution down on the peninsula. Where he was present at the birth of Google. Sergey and Larry were classmates of his. He decided to go into a much more profitable field of robotics. No, it's just a matter of timing, right? So the search business was very big, in the last 10 years, but robotics is coming up. And speaking of timing, Steve always gives interesting talks, and I had a pleasure of listening to him give a talk recently that was he set the talk in the year 2040. So the whole talk was him looking back over the history of what happened over the last 40 years in robotics. It was terrific, and it was very sci-fi. Steve has a background as an engineer, as an entrepreneur. He's led major research teams on human-computer interaction, both at IBM, Almaden, and at Xerox PARC. So two of the great places where you would do this kind of work. And he really played a key and instrumental role in the founding of this terrific company, Willow Garage, that is really transforming the field of robotics. And I can speak, I see many of our roboticists here at Berkeley, our faculty are in the audience, and I hope I'm speaking on all of their behalf that that company is transforming the field. They are establishing a platform that researchers are using around the world. It's providing commonality and an open source attitude that is really accelerating progress in this field. So we all owe him a great debt, and I'm excited to hear what he's going to talk about today. Please join me in welcoming Steve Cousins.
Thanks so much. It's going to be really, really, really hard to live up to that intro. I was thinking as he was talking, I'd like to meet this guy. And I'm honored to be here. I've known about CITRIS for a long time. It's my first CITRIS seminar, but I noticed that my former boss at IBM, Laura Haas, gave the talk last week, and a former colleague from Xerox PARC, Marty Hurst, who's a faculty here now, is giving the talk next week. So I feel like I'm boxed in a nice way. What I want to talk about is open source robotics, and this is actually a pretty big change for the field of robotics. I was at a conference a couple years ago, and since I come from a company, people assume that this is the industrial side, so I get invited to give a talk on the industrial forums. And at the industrial forums, they ask you questions like, what has the downturn in the auto industry done to your business? Right? And for me, the answer is nothing, right? Because we sell robots to academic research institutions right now, and we're trying to create a whole new industry, a whole new way of using robots that's not in the automotive industry, but is more out in the world we call personal robotics. And so we've kind of changed in the period of maybe the last 2 or 3 years. The questions that get asked have changed from, what are you doing, what's the automotive industry doing to your business, to how are you using open source, right? And that's a pretty big fundamental shift in the kind of questions that people ask to industrial robotics companies, of which we're only marginally an industrial robotics company, I'll say that. So let me say a couple words about what we're trying to do as a company, because Willow Garage is pretty unique. And then I'll talk about the product and the open source robotics and what how we're trying to get there. We take as a fundamental, this is one of those things. Click? No? Change? Okay. Spacebar. No? Okay, good. I need a robot to do that, exactly. Then I could wander around the stage. So we take as our mission to build a new industry. This is a modest goal. And the important thing about this is we don't want to own, we're not trying to create a product and basically get everyone in the world to buy our product. Instead, we're trying to say, let's create an industry, get lots of companies involved, and we'd like to have some of the companies in that industry as well. But we're not trying to own the industry. We're not trying to take over the world and create a monopoly or anything like that. I put this next slide up once at Willow in an internal talk, and I had the title on it that said business model, which is a great business model if you can do it. That doesn't tell you much at all, but everyone laughed. And the interesting thing about this slide, you think about industries growing, you think about like the internet and it took off. Nothing actually grows like this, right? What actually happens is something more like this. You go up for a while, but then you kind of tail off, right, in the long term. And the reason is that, of course, if you grew exponentially forever, eventually you just consume all the energy, all the money in the universe, and that's not possible. So this is what growth curves look like. And then the reality is actually even a little bit more subtle. This is just by way of background. When you actually see a new industry grow, what typically happens is that there's a bunch of technologies that grow together to form that S-curve. And the technologies each have their own little S-curve. And so the easiest way to think about this is from the chip industry. You go back to when computers were made out of boards. Just a memory was just a board, and everything was a board in a computer. Then we got down to chips. We had TTL logic, and then we had CMOS logic. And each one of these technologies had its own performance curve. All together, we put those together. We call that Moore's Law, right? And Moore's Law has given us price performance in computing that's consistently doubled every 18 months or so over the last 30 or 40 years, and that's a pretty amazing thing. So just with that as background and trying to grow an industry, I'm looking at some of the technology curves that are coming along here and thinking about the new industry of personal robotics. Let me take one more step back in history, and then I'll come back around to the robotics side. Actually, this is a robotics step. This is a video from 1966. I don't know if you recognize Johnny Carson. Johnny Carson was a late-night television host for a long time. He's smoking on TV in California. This is obviously a long time ago. And he's talking to a guy named Joe Engelberger there. And Joe Engelberger is widely considered the father of robotics. Joe's introducing this Unimate robot. It was the first industrial robot. And what he's showing here is, first thing is you get a sense of the size of this thing. It would fill this stage. The second thing, I don't have the sound on, but if I turn the sound on, what you would hear is when they turn the machine on, they stop talking because it's so loud. And the other thing that's really scary to me is that Joe Engelberger walks right next to it while it's turned on, which is something you would never do in industrial robots today. He shouldn't have done it then either. But I think at that point, nobody had ever been hit by one. And you go on to introduce this robot, and I'll let it run until it does its first trick. But the conversation that goes on around this technology is all about how it's going to replace jobs, right? So in 1966, the first thing the robotics industry starts talking about is how they're going to replace jobs. And the gag, if you know these late-night television shows, there's always the host, and then there's the band leader. And so in this one, of course, the band leader is always the one who's the butt of all the jokes. And so the robot, after it does this trick, picks up a wand and starts directing the band. See, the band leader's job is going away too. Just to understand the technology here, we can move the robot precisely. That one wasn't even that particularly precise compared to some of the latest robots today. But in the industrial robot space, you have this ability to basically move an end effector from one point to another point. And over time, over the last 50 years, we've gotten very fast. We can move the end effector really quickly from point A to point B. We can move it, we can carry heavy loads, so you can lift huge glass wafers, because you can design the robot to do that, or you can lift up whole car bodies, so you can be strong. It can hold on to welders and basically hit the same sub-millimeter precision spot over and over and over, do spot welding. And most of cars today are built using the descendants of this robot. If you go into a Toyota factory, about half of the work is basically done completely robotically, from the time that a roll of steel comes in until the time that painted auto bodies are rolling along and need to get the interiors put in, is almost all completely automatic. Here's another important task, being able to get a beer and pour it. And you can see this really successful. But the interesting thing here is that all of the tasks, first of all, the interesting thing is you'll still see demos today in robotics of people pouring beer and stuff, including some of ours. And also, this is completely blind work, right? This is blind robotics. And one of the leaders of the industrial robotics companies, one of the biggest robotics companies in the world, Yaskawa, which makes this Motorman robots, basically said to us recently that there's almost no blind work left, right? All the things that you can imagine where you basically close your eyes, pick up at this spot, put down over here, or hold this welder here and activate it for 2 seconds, or whatever you're going to do. All that work has basically been done in factories. Now they're looking at the next level, which is how do you apply perception to that. So as I look at robotics, and the vision we have is let's get robotics out of the factories and into the world. So currently robots sit behind fences in factories primarily, except for Roombas. Roombas is a nice, interesting exception, and maybe like the first S-curve on the industry that I'm talking about. The other technology is interesting is computer servers, right? So servers, of course, you all have powerful computers in your pocket called a cell phone. But servers, the things that run the internet, are also extremely powerful, and they're also hidden off in server rooms, right? So how do we get that powerful computation ability out into the world in a way that it can actuate itself in order to help us? And that's the challenge. From a software point of view, there's 3 things: navigation, perception, and manipulation. Navigation means how do I get the robot from point A to point B robustly without getting lost, without getting stuck. Perception means how do I build a model of the world? And this turns out probably the hardest of the 3 problems. How do I build an accurate model of the world so that I can understand what to do, what I can manipulate, and then how do I manipulate objects in that world? I'm leaving off AI, right, that sort of high-level intelligence, as I think we can do a lot with these 3, and one more, which is integration, right? So the other problem with software and robotics today is that we're pretty good at navigation. We're working hard at perception, but that's a really specialized skill. We're working hard at manipulation. That's a different specialized skill. And putting all the pieces together is a different specialized skill, and it's a hard problem, and it's something that also has to be done. So with that as kind of background, we set out 5 years ago, Willow Garage, to create basically autonomous technology that we think could help the world. Get those robots out of the factories, get computers out of server rooms, and get technology helping people more than it was at the time in a new area. And one of the things, we played around with the DARPA Urban Challenge. We had a car that was an entrant in that. And we were actually playing around with making an autonomous boat. And we saw this project at Stanford with a robot that was also designed to be autonomous. And the argument was, this is Eric Berger, who was one of the co-designers of this. And the argument was, if you can make a robot that's safe, so it starts off by hitting them, and the other designer you'll see in a minute, Keenan, is going to get fed by the robot, so that indicates how much he's trusting this, right? You don't do that with an industrial robot arm if you want to preserve your head. So they designed this robot on the argument that if we want to make progress in the software of robotics, and that's really the interesting next step, we have to have a robot to do that research on, and there are no robots like that. And so they built this robot. The interesting thing about this robot is prototyped almost completely out of plywood. Laser cut plywood turns out to be a great prototyping medium. And you can see that this is a little bit sped up, but this robot's actually doing interesting home tasks and is capable. Now, I need to say, this is being done completely under human operator control, right? So Eric is sitting in the same room with this robot. He's using 2 Phantom Omnis to basically control the arms. Whatever his arms do, that arm's going to do. And he's doing this, and he's a reasonably skilled operator. And he's in the same room. The same room means he doesn't have to have great sensors on the robot. He can see what's going on, and he can hear when something hits the ground. Nevertheless, a pretty impressive piece of technology, and especially the arms, which are, as you can see, reasonably reasonably safe to be around. The argument that Eric and Keenan made was that we need freedom, that researchers need freedom to focus. That if you go to a graduate school, and 5 years ago this was definitely the case, you spend a long time doing this required engineering, the work that you have to do to get your robot working and your fundamental software working so you can get something turning over. And then at the end there, you can do a little bit of research, right? That's your dissertation work. So for the last year of your thesis work, you're actually doing something new and interesting. The rest of the time, you're basically reinventing the wheel. And if we could build some software, which we call the Robot Operating System, or ROS, and a robot like the PR2, which I'll show you in a minute, the idea was, well, you could start by learning that platform, but it doesn't take that long to learn the platform, and you get a lot of benefit. And then you can spend the rest of the time doing work and adding to the field. And by changing the equation like this, changing the balance of how much time PhD students are innovating, we would be able to speed up significantly the advancements, the field, and basically create an industry faster. So we took the idea that Eric and Keenan had again was, and they worked for Andrew Ng and Ken Salisbury at Stanford. The idea that they all had was, let's make 10 of these robots and give them away to top research labs in the world. So we created the PR2, and we did actually give away, we couldn't decide on 10, so we gave away 11. And we also kept another 10 in-house, and we started selling them. This is the PR2 robot, and this is some navigation demonstrations. This is actually a sort of montage of videos of different kinds. But here you can see the robot navigating, avoiding things on the floor. Sebastian Thrun, who was the leader of the Stanford team in the DARPA Grand Challenge, once laid down in front of the video, in front of the robot, to see whether the navigation actually worked. And it almost ran him over, but we fixed that. Now it's stopped for a chess piece. This is plugging in. Plug and play, exactly. Actually, we took this capability, this ability to plug yourself in, and combined it with the navigation capability, and had the robot do continuous operation over a period of 2 weeks, so 140 kilometers in 2 weeks. This is probably the most famous PR2 video ever. Well over 500,000 hits on YouTube now from Peter Beal's group here, folding towels. And what I always point out about this video is that if you want to get a video on YouTube and you want to get a lot of hits, what you need to do is this move right here. That's the move, right? Do that move and everybody's like, wow, that's so cool. So Peter was able to do 50, or Peter and his students were able to do 50 towels in a row. This is a little hackathon that we did just to kind of show the generality. The PR2 was not designed to play pool. But we did this little hackathon. We spent 1 week and said, in a week, can we make it play pool? And the answer was yes. We actually got it to make some nice long shots. This is another, some work that's going on with the PR2, also part of that beta program, the robots that we gave away in Munich. And they worked really hard to make the robot serve pancakes, make and serve pancakes, in Michael Beatz's group there. The PR2 was the robot. There was 2 robots working together. The PR2's job was to go to the refrigerator, get the pancake mix, bring it over to the cooking area, and then the other robot actually did flipping the pancakes, and then the PR2 delivered it. They were able to serve 4 pancakes in an hour. So watch out, short order chefs. This was another quick hackathon. This is called Beer Me. Another 1 week at Willow Garage, we said, let's show the power of the platform. Let's see what we can do. Can we have it bring us a beer? So there's a web interface, and you drag what kind of beer you want, and the robot goes to the fridge, opens the refrigerator door, pulls out the appropriate beer, so it actually did a little bit of object discrimination, and then we actually put a cup holder on the robot just for that project. And then go close the door. This is one, again, another important thing. This video also gets a fair amount of hits, surprisingly. And this thing you need to teach your kids. Always push it close at the end. And then use the navigation capabilities so that you could drive it to the other room and hand you the beer. And so this was, again, a 1 week hackathon. Not something that we use every day, thank God, or we wouldn't get much work done. But it's sort of a demonstration that the platform is reasonably viable and gives you a sense of the state of what you can do autonomously. And I should also say what you can't do autonomously. And that's, doing this on a day in, day out basis is challenging, right? There's a lot of failure cases. And so I don't want to leave you with the impression that, robots basically solve all problems. This platform has a couple of issues. The biggest issue is it's expensive. It's about a list price of $400,000. So it's not like everybody's going to put one of these in their home. The other issue is that it's kind of big. It's actually, there's a clever design decision, which is it's on wheels, not walking, which means that it can go basically anywhere that a wheelchair can go. So its design constraints are be able to go up a wheelchair ramp, fit through the doorways that are the Americans with Disabilities Act specifications, and open doors that match those specifications. And that's actually, it's a nice benefit, sort of like curb cuts helping bicyclists, right? It's a nice benefit of having a platform. Okay, I'm going to show you, this is a different robot, and in the course of the work on the PR2, near the end, we came up with this telepresence robot. And what I want to say about that, I'll just go back, I think, and just pause, forward, space. Sorry. Okay. So latency is a real problem in user interface design, I can tell you. Come on. I have no idea where we are in the presentation. Slides. Okay. So what I wanted to say about this is a. Okay, this is the least. I'm going to go back to the other one. This is the least expensive robot that you can come up with that really takes advantage of the robot operating system. And I'll say more about the robot operating system in a minute. But when we built the PR2, we actually built two things in parallel. We built the hardware, and we think of ourselves primarily as a software company, but you have to have hardware in robotics to do software. And so the PR2 was a platform that was pretty rich. The Turtlebot is a pretty inexpensive platform and much less powerful. It uses basically a Roomba for the base. It's an iRobot Create. And a Kinect sensor, which came out about a year and a half, 2 years ago now? Or 1 year ago. 1 year ago, yeah. Kinect hasn't been out very long. And the Kinect plus the Create gives you the ability to basically move around and see the world in 3D. And so we added an inexpensive netbook, dual-core Atom kind of processor, and a little bit of custom charge board, but really, really simple in the robotic space. And now you have a platform that, for $1,500, somebody can buy and use in a class or something and run all of the navigation software that has been contributed to ROS over the years. I'm going to try one more time to go back. All right. This is the tech site. So the tech site came out right as we were finishing the PR2. And we didn't intend to create another product. We had one electrical engineer who lives in Indiana. The reason we hired somebody in Indiana is not so that I could pay taxes in multiple states, but it's because he was just good, right? We had a problem that we couldn't solve any other way. And the problem was to build basically a motor controller board that was small enough to fit throughout the PR2. And we tried outsourcing it, having somebody build it for us. They couldn't do it. We tried building it ourselves. We just needed more expertise, and we found this guy who could do it. So we hired a guy. His name is Dallas Gecker. And Dallas lives in Indiana because he wants to. I asked him, why would you want to live in Indiana? And he said, he has a house bigger than mine. So, okay. But it's still Indiana, right? I grew up in Chicago, so I understand why I wouldn't want to live there. Anyway, he lives in Indiana by his own choice. And he wants to be part of Willow Garage, which is here in California. And there's 60 of us sitting in Menlo Park and one of him over in Indiana. And so he's the electrical engineer inside the box, so to speak. He's inside of a Polycom, when you go to an electrical engineering meeting. And for most of the company, who is software people, they don't know him at all. So he's basically not a part of the company in any real sense. He's an employee, but most people in the company haven't met him. They never see him. Even the people who he's working with only hear his voice through this Polycom. And so he doesn't like this situation. And so he says, can I just Skype into a laptop? So they put a laptop at the end of the table with Skype, and suddenly you're able to see his face, which is better. But if you ever used Skype from a laptop in a big conference room, what you know is you have this kind of narrow view, and a little thing at the end there, that's the screen, which you can't really read. And you can't see the people that are sitting next to you, and you can't turn your head. And so he said, well, can I get a better camera, like a pan-tilt camera? So they built him a little cart with a computer on it and a little pan-tilt camera and said, there you go, that's pretty good. And at some point they realized, wait a minute, we're a robotics company, we can do better than this. They took the caster from the PR2 robot and mounted it on some 80-20 framing, basically Tinker Toys for adults, put a car battery at the bottom, put a computer on it, and a big LCD screen like you saw. And suddenly, Dallas's life changed in terms of his relationship with Willow Garage. Suddenly, he's able to wander around the building on his own without having to say, will you set up my laptop? He could, before, like I said, I didn't even know what he looked like. But now after this, I start to see him in the hallway. I say, hey, Dallas. He goes, hey, Steve, right? And we pass each other. And it's like, okay, not the most important interaction in the world, but nevertheless, I know that he exists. The tech size the robot's about this high. And so I get used to seeing Dallas here. And he would come to lunch. He wouldn't eat, but he could come to lunch. And we had stand-up meetings. He could come to the stand-up meetings. And importantly, he could come to seminars, right? So this seminar's special. And of all the seminars that are out there, some of them are broadcast like this, but most aren't, right? And in particular, just talks that you have around a department or something typically aren't televised with the infrastructure that this seminar has. And so Dallas typically couldn't go to those, right? Couldn't go to those talks, or if we had an all-company meeting, he couldn't be there unless he specifically asked somebody to please bring a laptop and open me up. Now with this new technology, he's able to show up in the room on his own. It's a little bit awkward, right? Because like, where do you park the robot, right? I mean, think about it. He doesn't want to be way in the back because the camera's not that good. And if he sits right in the front, you can't see, right? So he tends to sit off to the sides. But those are solvable problems. The point is he has his own ability to work. And so this was a distraction from finishing the PR2, but not a huge distraction. I mean, we were able to finish anyway. And that robot that we call the TechSci after Dallas became our first spin-off company. So as I talked about growing an industry and sort of spinning off companies into this ever-growing number of robotics companies, we hope. This was our first company in that space. Okay, so I'll just come back to this slide for a minute. I mentioned this notion of linked S-curves, and I think in the home, in personal robots, task-centered is the beginning. This remote presence robot is the next level. Being able to act at a distance is, and I'll come back to this, I think is the next step after that. And then eventually, some kind of full automation. The point is, we're not going to see Rosie the robot in your home tomorrow, right? It's expensive. The software's not there yet. But if you solve the AI problem by basically letting a person come in sometimes, that matters. I mentioned we did it's called a continuous operation demonstration. We had the PR2 run for 140 kilometers over 2 weeks. The goal was just over 100 kilometers of operation autonomously. But we made an interesting rule. We said it's okay if you have OnStar, essentially. So the robot is allowed to ask for help if it gets stuck, but nobody's allowed to touch it. You're only allowed to help it remotely, right? Because we think that's very plausible, given the cloud, given things like a Mechanical Turk, right? It's possible to say to the world, hey, all you people who are online right now, can somebody help this poor robot because it doesn't know what happened? And in the course of 2 weeks of continuous operation, the robot needed help twice, right? And they were typically things like somebody left a cord on the floor where it didn't expect it, and it didn't see it, tried to go over it and got caught up. And then the person's able to drive it, run through some, people are really good at control. So you can actually get your car out of a snowbank when there's no way an autonomous system is going to do that. Sebastian's self-driving cars at Google, right, aren't going to get out of a snowbank on their own, but you can. And the other one is it can get mislocalized. So just the sensor inputs are still not that great. The perception of the robot's not perfect, and so it can get confused about where it is. But in the course of 2 weeks, it got stuck twice. And the point of showing that Turtlebot video, the little Roomba thing, is that the same software that's running on the PR2 also runs on that, right? So we've now got a software base that's completely open source under a Berkeley BSD license, and is available to anybody in the world to run on different robots. And that's been a big deal. So this robot operating system, we created it for the PR2, but one of the first things we found out is we tried to work with we knew that we wanted to do this in an open source way. We wanted to try to build a community. And one of the first things that all the graduate students and professors around the world said to us was, hey, we don't want to just give you our code and then have you publish it and take credit for it, right? We're academics. We have to get credit for what we do. And so we created this notion of a ROS repository where any institution or individual can create their own repository, and the ROS system builds robot software out of a federation of repositories. In other words, we're able to index all those repositories, pull stuff together at build time, but when you want to point to what you did as an institution, it's in your own repository. And so this is a chart of the growth of repositories since we first started this in 2008. And you can see it as of like late 2010, we'd gone up basically exponentially. Another way that we measure ROS, we actually try to measure it in a lot of ways, but another way that we measure ROS is packages. So when you're trying to get a lot of people in the world to contribute to a common code base and kind of develop it together, you need to basically come up with some kind of small module, some small units. And so in ROS, the unit of code, of functionality is a package. And a package is supposed to do one thing, as small of a piece of functionality as possible. This chart's actually a little bit out of date. By now, there's over 3,000 packages. So the good news is there's like 3,000 robotics packages that you can download for free under a BSD license. And the bad news is there's like 3,000 robotics packages that you have to sort through when you're trying to figure out how to build something. There's actually layers above this in ROS where software gets combined into things called stacks. And stacks are high-level pieces of functionality. So the navigation stack was the first and most important one. But there's also a stack to do arm manipulation. So if you know about robotics, one of the challenges is that some of the motion planning problems are actually NP hard in the number of links. So when you're trying to do motion planning in a plane, like basic navigation, that's a problem that's computationally tractable. If you want to actually figure out how to move a robot arm from point A to point B without hitting anything in the environment, that's actually not computationally tractable. And you end up using stochastic algorithms to do that planning approximately. And then you do smoothing, and you do there's a whole bunch of steps. It ends up being what we call an arm navigation stack, or a arm moving stack. And there's a lot of complexity there, but what we've been able to do is pull together work from some of the top universities where research is going on in planning, have students from those labs come together and work together as interns at the same time, and then release code that is available to everyone to use. And as a result, what's happened in the last few months is something called ROS Industrial, where all those industrial robot arms, the descendants of the robot I showed you at the beginning, are now able to run the most modern research code, and obviously hardened versions of that, in order to do planning more effectively. And it's something that is really, really surprising, because you would think in an industry where they're using robots manufacturing to basically make a difference and make money every day, that they would have the latest and greatest. But it actually turns out it's different. The criteria are slightly different. They're very conservative. The goal is 5 nines of robustness. So I want to make sure I can do this over and over and over again. But it's not so much that I want to be able to program it really fast. Or at least it hasn't been until we got to the current era where suddenly people are saying, you know what, for US to be competitive in manufacturing, we need to deal with the small runs. And you can't do a run that's going to take you 48 hours to do a whole batch of material, only 48 hours. You can't set up a line for that, right? You need to use what you have flexibly, quickly, now. And to do that, having the robot plan the path instead of having a programmer spend 4 hours planning the path is a big difference. We think in the PR2, when you see some of the demonstrations, I get frustrated because I say, oh, why did it take 5 seconds to plan that path, right? But if you think that it would have taken a person could plan the path fast, but to program the robot to do that path might have taken him, an hour or longer, depending on who he is and what skills and what robot he's using. Remember that if you're using an industrial robot arm, you're not allowed to turn it on if you're within the workspace. So you're having to do it all remotely with some kind of a joystick. Anyway, the point is that ROS is now being used on industrial robots. It's also being used on a lot of other robots as well. This is the PR2. This was a one-weekend hackathon. The robot taking input from MIDI file. That was the robot I mentioned flipping pancakes, it's also running ROS, the robot operating system. That's in Munich. Here's a robot running ROS at University of Pennsylvania, controlling a quad rotor. They do some really cool stuff. This is a robot at Stanford, another plywood robot, an early arm by Morgan Quigley. He's one of the fathers of ROS. Here's a robot out of France called the Now, running the ROS navigation stack. This is a robot out of Germany called the Carobot, running ROS. This is a little robot that goes through pipes to clean them using magnetic techniques. This is a car running ROS. You get the idea. There's a lot. Basically, it's not that I don't have any idea why you have a surfboard running ROS. And I don't have the video. I should have the video. I need to get it and add it to this. There's actually a rat running ROS, and I don't know why. This is Lego's sort of the smallest robots that a lot of kids have access to. The point is that ROS is a general purpose platform that lets you basically pull pieces out of this huge software repository and get them to work together efficiently. So, and ROS is, again, completely open source and available for commercial and non-commercial use. And that's meant that people are willing to contribute to it in a significant way. So I just want to, I think I mentioned already that the notion of a robot being completely autonomous is like a pipe dream. It's a great idea, but it's going to take a long time. In the meantime, robots can be really valuable in the short term with human in the loop. So we mentioned the OnStar kind of example. But let me give you a completely different example that I think is probably the most inspirational use of robotics that I've seen. This is a guy named Henry Evans. And Henry was the CFO of a Silicon Valley startup until he turned 40, and he had a brainstem stroke. And was left a quadriplegic, and he is mute, cannot talk. He communicates with his wife by looking at the letters on this board, and she reads them out so she can read out robot. He can also communicate by moving his head and having a camera on his computer track his eyes or track his head in order to basically control a mouse. You can see he can move his finger a little bit to click the mouse. So Henry was watching CNN, and he saw the PR2 robot on there and said, you know what, that could make a big difference to my life. And so he called us up, and he called up Georgia Tech, Charlie Kemp's lab there, and said, can I get one of these? Can I use one of these to help me out? The first thing we had him do was pick up things on a table using a web interface that he was controlling. And then the first thing he wanted to do was turn the robot toward himself and put the hand in his face. And we're like, that's scary, right? You don't put robots' hands right by your face. The reason he wanted to do that is he wanted to scratch his face, right? Because if you're a quadriplegic, you still get itches, right? And you can't scratch them. The next thing he wanted to do was shave himself, right? And so all of a sudden, and we actually put a force torque sensor on this so that we could measure how much force he's using versus how much force a human's using when they shave him. And it turns out his wife pushes 10 times less hard than he does. And so it's obviously why he wants to shave himself. And then this was the other thing he can do. So he can using the PR2 and sort of current interfaces, he can control the robot in another room. So this is different than the PR1 videos in the sense that in the PR1 videos, the one I showed you with Eric and Keenan at the beginning, Eric was sitting in the same room. In this one, Henry's sitting in a different room, and so the sensor suite has to be much better. But the result of this project has been that Henry sees a future in which he can actually manipulate the world. The things he wants the robot to do, besides shave himself and be able to do some basic self-care tasks, the biggest thing he wants the robot to do is something the PR2 is not ideal for, and that's he wants to do a comedy routine. Right? He's actually a very funny guy, and he can't express himself very well or very efficiently. But if he's able to have a robot sitting here, and he's able to sort of pre-plan some scripts, he should be able to basically have the robot do things and use his human instinct about the timing, which is something the robot wouldn't be good at, in order to deliver lines at the appropriate time and respond to heckling and so forth. But that's one of our challenges. We actually we took PR2 and Henry out to Stanford Shopping Center over at Halloween because they have kids coming through and doing trick-or-treating. And there was a long line of kids who wanted to get candy from this robot that Henry was controlling. And it was a kick for him because he was able to get out and actually participate. So this, to me, is just a really heartwarming story. So let me end with, back to this picture that I started with. If these are three big problems in order to get robots into the world and used more efficiently, the current state is that navigation with the navigation stack in ROS, you can see that as kind of a solved problem, right? In fact, when we started Willow Garage 5 years ago, the academic community said it's a solved problem. So we spent a few years and solved it. Well, there's always solve and then there's engineering, right? So we know what to do, but you got to engineer it. The integration problem, I think the robot operating system has come a long way. I showed you the growth charts, and if you go to a robotics conference and you ask people, are they using ROS, there's only a few people who aren't, and the reason they're not using it is because they have something else. They've got a long history, and they've already had technology that they've been using for a long time. But everyone talks about when they're going to convert to ROS at this point. I'm really proud of that. What that means is that there's a common platform. So when people in robotics decide to work together, the barrier to doing that is much, much lower than it used to be, than it was 5 years ago. In the perception world, one of the big unsolved problems for robots is object recognition. There's actually some good progress here, but I wouldn't say it's a solved problem by any stretch. On the manipulation side, there is a grasping pipeline that's getting better and better. I gave a talk like this at Santa Cruz a couple weeks ago, and I brought the PR2 with me. See, I didn't bring it here because you guys have one already. But I just set the robot next to a table and turned on the grasping demo, which basically picks things up from one side of the table and puts them on the other and picks it. And it doesn't have any idea what's there. It just says, oh, there's a table. Let me see what I see. And it looks at this half of the table. If there's something there, it picks it up and moves it over. And so we just set like the remote control for the projector down. It just picked it up and moved it. And somebody gave me a paper cup and it crushed it. But it picked it up successfully. It doesn't know that you shouldn't crush paper cups. Or you could look at the bright side. It didn't put its finger in the drink. In any case, the woman didn't want it back. And then the last thing is that between perception and manipulation, which are both, this problem is getting solved, this problem is still far from solved, but human in the loop makes a big difference, right? You can easily imagine when you're trying to do object recognition, if you're not sure if the robot's not sure what the object is, it can send a text out to somebody or put something out on a website and say, hey, can somebody identify this? Or put it on Mechanical Turk and pay somebody a nickel to tell you whether it's right or what the thing is. And so human in the loop actually, I expect, is going to make a big difference in robotics over time. So, I guess I'll stop there and see if anyone has any questions. And thank you for coming.
So do we have any questions? Okay. So use the mic if you don't mind so that the people watching online can also hear the questions.
Yeah.
So just a general question for you. Seeing as Willow Garage, I guess, has one foot in the world of industry and one in the academic world, how have you dealt with challenges of, you hinted at this at the beginning, of kind of what is theoretical research versus what is just implementation and just engineering? And do you have any rules of thumb, or is this a continual challenge in working with academic partners?
So it's not a challenge in working with academic partners. What we basically, I'm happy with academic partners to solve any problems that they find interesting, right? What I try to do is look at what can this robot do, and what can it do, and how do I make it do more than it, and also what should it do, and how do I move it in the direction of being able to do more useful things. So one of the challenges that we've just given to the community is something we call the Sushi Restaurant. So the Sushi Restaurant goes like this. There's a space not much bigger than the stage. There's a table where people would sit and eat, and with chairs around it. There's another place where dirty dishes go. There's a place like a cabinet with clean dishes. And there's a round rotating table that kind of simulates the sushi boat, right? And the robot's supposed to come in, clear the table of all the dirty dishes, put them in the dirty dish area, take dishes out of the cabinet, reset the table, and then go serve sushi off the rotating table. Those are progressively harder problems, right? So picking up things on the table in robotics today is reasonably solved, right? Picking up plates that are maybe hard to grab, maybe not solved. Getting things off the cabinet is a harder problem because you have to navigate around the walls of the cabinet and sort of unusual shelves, so it's a little bit harder planning problem. Picking things up off the rotating table, nobody solved that. right? That's stuck. Everybody assumes in robotics today that there's a static scene, and I get to plan for as long as I need to, and then I'll go ahead and grab something. If something's moving, now I got to take that motion into account. And so by coming up with challenges like this, we think that that forces the integration. It forces us to make progress. And it's really freeing for me to be at a company instead of a research lab. So when you're in a research lab, you have to say, well, what did I do, right? And when you're in a company, and especially with the stance that we're taking in open source, I want to say, what can the community do? So I didn't say we're doing this project, the Sushi Restaurant, in-house. We gave that as a challenge to the community. And there's people at all kinds of universities who will solve pieces of it, publish papers on that. But at the end of the day, as a community, we've made progress, right? And that's, I think, what matters.
Oh, we have a question in the back.
These robots have the capacity to either mitigate boring tasks for people or make what we're doing easier. If you could articulate how you think robots can contribute to efficiency and sustainability and how you've contributed that, what would that be?
So I mean, one of the things that I think, and Ken mentioned my talk about sort of looking backward from 40 years in the future. One of the things that I talked about there was the notion that we may get much more decentralized as a society. And robots can actually help that. So we don't, instead of shipping food, you know, halfway around the globe so that we can have fresh fruits and vegetables, my guess is we're going to find ways where using robotics we can tend gardens, maybe indoor gardens, locally and basically produce things more locally, which is one way that I could see sustainability happening. You know, I think this is not a utopian technology by any means, right? I can definitely see, you know, and this is true of all technologies, right? When the car comes out, lots of good things happen. The automobile, lots of bad things happen, right? The buggy whip industry is totally decimated, okay? And we put up with that, right? And the computer comes out, and secretaries essentially go away, right, as a profession. I mean, there are some, but not very many, not like there used to be. And so work shifts, skill levels go up. The same thing's going to happen in manufacturing. And I don't say it's going to happen without problems. But I do think that, you know, when you can do things systematically, repeatably, you can handle things in ways that are good for the world if you treat the technology appropriately. So, you know, dealing with a recycling stream in an efficient way so that you can get maximal use of reuse of the matter that we're consuming as a society is something that robots would be really good at, right? And this is another example.
So do we have any other questions? Oh, here we go.
Thank you very much. Hopefully a robot will not replace the microphone carrier soon. Thank you very much. And I wanted to ask, there have been press accounts of robotic surgery, which surgeons actually welcome rather than fear. And I was wondering whether one can imagine, first of all, ROS being used for that, and can we imagine repositories of surgical procedures that surgeons can just pull off the web or something like that? Thank you.
Yeah, I think, you know, the biggest question in robotic surgery is liability, right? Unfortunately. Technically, having a robot do the motions that some surgeon did, repeating those motions is relatively straightforward. But if you look at something like the intuitive surgical systems, Da Vinci, those robots only do one thing autonomously by FDA rule. The only thing that they're certified to do is pull out, right? They're not allowed to do any actual surgery. Every other bit of cutting and twisting and tying knots and whatever they do is done by a surgeon, and he's directly operating that robot. And that's primarily for liability reasons, right? And so we're going to have to face as a society over the next 30 years questions of what are we willing to let automated systems do in the world next to us, right? Are we going to let automated cars drive? And there's a huge benefit, right? I drive in rush hour every day, and it drives me crazy, and I would be much happier if I could read a book while I get transported. But today I can't do that because even though I've actually ridden in the Google car, right? I know that the Google car could take me from work to home. I believe it's safer than driving with my 16-year-old. But that doesn't, you know, that's not saying much. You know, I'm not going to be allowed to do that for some years, right? And the same thing with the robotic surgery. And I think that's just an interesting question that we're going to all have to deal with and figure out ways we can say, yes, I'm willing to cede this capability to automation because that'll be good for us as a society as a whole.
So I'd just like to ask about generality in the sushi restaurant problem. And this is something we faced in the planning competitions in AI as well, which is that whenever you set up a competition, people will special purpose engineer a solution that wins that competition, but if you change the conditions even slightly, it falls on its face.
Yes.
And how do you avoid that problem? I mean, really we want to be able to send the robot into any sushi restaurant or anyone's kitchen and have it deal
Yes.
with the configurations and the stacking and whether it needs to use a tray or doesn't have a tray and so on and so forth. So
Yeah.
how do you work that?
The only way to do that is to underspecify the problem and make the researchers mad at you, right? I mean, you like one thing, you know, with the sushi restaurant, I gave you a vague description, right? Which, as a human, if you came in, I have a restaurant at Willow Garage, it says called Yesterday's Sushi, and nobody eats there. And you could come there and you could immediately do this task, right? In fact, I have a video of the PR2 doing this task under human control on the very first try, right? Completely is able to do that task because it doesn't have any question of where's the table. So one of the things we do is we don't give a map of the room. We just say, look, there's a table with chairs around it, that's the table. There's a table with no chairs that's up against the wall, that's the dirty dishes area. There's a thing with multiple shelves against a wall, somewhere against some wall, and you have to figure it out, right? So you get generality by underspecifying. The other thing we do is, an earlier challenge that we gave to the company was, go into 10 different rooms and plug yourself in 10 different outlets, right? So by not doing one outlet, we were forced to train on the building. Now, it turns out that same code doesn't run at Stanford. They were trying to get it to run, but they have different outlets, right? And so the training for that outlets isn't general enough. Probably the right thing to do would be to say, I want this to run at all the PR2s everywhere in the world. Then you deal with European outlets and stuff, and it starts to look really different. But eventually, you can generalize by pushing. But you're right, it's a hard problem. You solve the first one, and then you make it less specified and try to solve another one.
Okay, we have time for one last question.
Great talk, Steve. I'm curious about if you could say a little more about the idea of the cloud and learning in this, maybe to follow up on the last question, which is, to what degree could you envision that all the PR2s could share all their information and sort of live happily together as a society?
Well, PR2s are programmed to be happy. No, happiness is not actually a word, but I mean, word that robots use. But sharing information is another pure policy question, right? Like, if the robot's willing to dump all of its information onto a web page that's accessible to all the other robots, the equivalent, technically it's no problem to do that. When we actually sent PR2s out in the world, the first 11, it was amazing how what the concerns of people were. Like, well, this is a robot, but my institution, my university says I have to put it on a special robots-only network because I don't want robots on the main network, and so it needs to be isolated out. Well, that means it can't talk to the rest of the robots in the world by design, but it's because somebody made a policy decision. Technically, if the robots are reasonably the same, it's easy for them to learn from each other and from people. So I think that, sort of to the heart of your question, the cloud is going to make robots smart a lot faster than somebody programming and programming and programming. And over time, more and more tasks will be doable. The tricky part is that when you program a robot to do a task, you tend to customize it to that. So the pool playing robot that we did works on the pool table that we have at Willow Garage. It's different than probably any pool table you've ever played on. It has like claw feet and stuff, right? And so detecting it's going to be slightly different. It's got diamonds around the edge that we use to figure out where the table is, but those diamonds are probably different than some other pool table. Maybe the color of the felt is different, right? In fact, it changes over time, and any of those things that are taken into account by the programmers won't generalize, and that's the trick to get over that stuff.
Okay, well, thank you again. It was a great talk.
Thank you very much.